We all need a little help from time to time, and the BigFix root server is no different. It's well known that a single root server can handle 250,000 endpoints. Its secret? A very capable assistant to help lighten the load. Let's talk relays. My name is Mike Consuegra. I'm the Director of Training and Content Development at AIS. But I'm also a longtime BigFix user, and by virtue of its innovative way of endpoint management, an evangelist of the platform. You can connect with me on Twitter at Mr. BigFix or on LinkedIn by scanning the QR code. Relays are the backbone of the BigFix infrastructure. In this webinar, I'm going to discuss their basic configuration, the methods that endpoints can use to communicate with them, and how to secure relays using authentication. First, let's get the basics out of the way. What is a relay? Broadly speaking, relays are smaller versions of the BigFix root server. Deploying them allows scaling of the environment without having to respec or change the hardware of the root server. Like the root server, relays register endpoints, gather site contents, and accept client downloads, but they also aggregate and streamline that data for transmission to the root server or even back to the clients themselves. Relays can also serve as caches for payloads that result from recurring client action downloads. A relay's basic function is to act like a funnel, collecting data from many endpoints. It is aggregated and organized in a way that can more easily be transmitted to the root server. But data can also flow in the opposite direction, from the root server through relays to clients in the form of patch payloads, software packages, files, or simple commands to be executed. From a practical perspective, all relays have the same functionality, whether installed on a server, desktop, on Windows, Linux, or even Raspberry Pi OS. From an architectural view, however, relays can have differences. There are two designations of relays that you can have in an environment. A top-level relay, sometimes referred to as a parent relay, and a leaf node or child relay. Child relays can be further subdivided into two logical types. Stock, which are typically used to manage up to 1,000 endpoints and can be installed on any of the supported operating systems. And high-scale relays. These can host up to 5,000 endpoints, but are generally limited to an install base of Windows Server and Linux on server class hardware. Let's look at a simple architecture. Relays can be arranged in several ways. This diagram shows relays deployed in a hub-spoke layout around the root server. In this layout, relays report directly to the root server, while endpoints report directly to the relay. In a more complex deployment scheme, relays can be arranged in multiple tiers, where leaf node relays report to top-level relays, and the top-level relays report directly to the root server. In this layout, leaf node relays can host other relays while at the same time hosting clients. It is this flexibility that allows easy scaling of the environment up to 250,000 endpoints using a single root server. Now, keen-eyed viewers will note an asterisk at the end of that statement, but it's not because I'm going to say the number is less. On the contrary, BigFix 10's modern client management capabilities allow an additional 10,000 compute devices per plugin portal, with a total of 5 plugin portals per BigFix instance. So in effect, that means you can have up to 300,000 managed devices using a single root server. Now, those of you that have implemented in large environments know that there are some caveats to those numbers. One of those is that top-level relays should not host more than 40,000 aggregate endpoints, or 120 relays. That means 8 high-scale relays at their full capacity, or 40 stock relays at theirs. You should also ensure that no leaf node relay exceeds their 5,000 endpoint capacity. This example is for a 20,000 endpoint environment with a maximum top-level capacity of 80,000 endpoints before a new top-level relay is required. The endpoints are reporting to their primary leaf node relays. Those are reporting to higher tier leaf node relays and ultimately to one of 2 top-level relays. The primary and secondary relay assignments means that one top-level relay aggregates data from 5,000 endpoints while the other aggregates data from 15,000 endpoints. Relays are powerful components of the platform, but they're also easy to set up. A relay is nothing more than a specialized BigFix client, which means that every relay has to be a normal client first. Once that endpoint is being managed, you can promote it to a relay by deploying a task from the console. The task contains 3 versions of the action that allow you to install the relay in the default location, specify the path where the relay code will be installed, or let the client pick the location based on which drive has the most storage available. But the actual installation is the easy part. Good architecture design and planning is essential to making your environment work. Some factors to consider when installing relays are location. Place your relays where they can do the most good, where there are large endpoint concentrations or bandwidth is limited. Where are the firewalls? Because BigFix only requires one port to work, it makes it easy to manage rules and allow your relays to communicate with downstream endpoints and other components upstream. Size your relay correctly. Before deciding what endpoint will become your relay, gauge the number of endpoints at that location. Be generous with storage. Relays will cache all content that passes through them. This gives them the ability to quickly redeploy that content without having to go upstream to re-download it. Give them the storage they need and configure them to use it. Even when placed correctly, some environments still have limitations, whether that's upstream or even downstream from the relay on the LAN. Relays can be configured to throttle their bandwidth in both scenarios. Let's look at some of the options you can use to configure this. If the bandwidth upstream from the relay is limited, you can use this client setting to modify the speed at which it retrieves content from its parent, whether that be another relay or the root server itself. If the connection from the relay to its parent is too slow for large downloads, it may be easier to let the relay download its content directly from the internet where available. These client settings can be used to configure that functionality. One allows the relay to go directly to the internet without checking anywhere else first. The second setting gives the relay the option to try to get the payload from the root server first and only download directly from the internet if that fails. Configuring the relay cache is another important consideration. Downloading directly from the internet won't be much good if the relay has no space on which to store the payload. By default, relays install with a 1 GB cache. Recent Microsoft updates all exceed that in a single patch. Operators can both monitor and manage this setting using analysis data and this task in the BES support site. Once you have some relays installed, endpoints will be looking to register on them. So let's explore the traditional relay selection methods, some less traditional that combine the best of both worlds, alternatives if the relay isn't available, and the relay equivalent of ghosting your endpoints. The simplest, and indeed the default way that endpoints select relays, is manual selection. In this method, console operators choose which endpoints will register on which relays. The most common options are for primary and secondary relay selection, but there are ways to assign tertiary relays and beyond. This option makes it less likely that endpoints will select other relays than those that are defined, and it's also quieter on the network, avoiding some of the chatter of the more dynamic options. Configuration of the primary and secondary relays can be accomplished from the console using the predefined relay selection slots. In the event that more relays are required for manual selection, a client setting can be configured to include a list of those additional relays. The client will attempt to connect to the primary relay. If that one is not available, it'll attempt the connection to the secondary, and if neither is available, it will iterate through the list in the order defined. The second traditional method clients can use to select relays is automatic selection. This allows clients to make their own decisions about which relays they should subscribe to. Relays are listed in the relay.dat file located in the Action Site subfolder of the client's data directory. Although the file is binary, the relay names can still be partially read. To completely decode the whole file, though, operators can use a BigFix provided utility called parse_relay.dat.exe. Although the process involves a sophisticated algorithm to pick the best relay, in simple terms, clients send out various rounds of ICMP packets to discover and register on the closest relay. When a client finds a relay during one of these rounds, it attempts registration. If no relay is found, another round of ICMP packets is prepared and sent out, and the TTL is increased by 1. Clients will continue to increase the TTL until reaching 20, at which time it attempts a connection to a failover relay or sometimes the root server. But there is a third option, one which combines the best parts of both manual and automatic selection: relay affiliation. Relay affiliation uses the automatic selection method, but by defining a subset of relays from which the client can choose in a setting called advertisement list, the operator can in effect allow the client to make its own choice about which relay to select, only within the parameters of that list. When configured with a seek list setting, clients will attempt to select from that subset of relays before attempting to connect with any others, even if those others might be more optimally located on the network. When a client configured this way performs a select relay process, it reads the seek list value and first attempts to register with the relays advertising that list. In this way, endpoints in the Florida office can be made to register with the Florida relay, and endpoints in the California office with the California relay. In this same scenario, though, only a few endpoints in New York register on the New York relay, because despite all being physically located in that office, the other endpoints are configured to seek out relays in different locations. The seek list client settings can also have multiple entries, each separated by a semicolon. So if the seek list for a client is defined as Florida New York, the client will first try to register on the closest relay advertising Florida and try New York only if no relays advertising Florida were found. Adding an asterisk to the end of the list gives the client permission to register on any relay that has no advertisement list defined, so in other words, an unaffiliated relay. But what happens when a client can't find a relay advertising the appropriate list or any unaffiliated relays? Well, it tries to register in the one place it knows from the moment it was installed, the root server. Now, this is not the ideal situation, so to mitigate this, it's always a good idea to set up a failover relay to intercept those rogue endpoints coming from a network location far, far away. Once installed somewhere that clients will be able to see it from anywhere in the network, they need to be told how to get to it. This is done with the client setting defining the URL of the relays so clients will know who to go to if they can't register anywhere else. If you have more than one failover relay set up, you can always use the failover relay list client setting to define a series of relays that will act as a failover. A failover relay is in effect holding up a welcome sign saying "Stop here if you're lost." But you can also define relays to do the exact opposite and actively ignore any client requests no matter how lost or persistent they are. This is a good setting to configure on top-level relays, since there are still relays that will respond to client registration requests, but in most cases you want to have only leaf node relays registering on these. Using this client setting will allow those relays to exempt themselves from being included in the relay selection roulette. Clients performing an automatic relay selection will not consider these as a landing site. Relay registration is basically a free-for-all when it comes to clients performing auto-selection. But there are times when you may want a bit more control on which clients get to register on which relays. The basics of authenticating relays can answer questions such as why you might want to secure communications. How do you enable this feature? What does a typical key exchange between client and relay look like in this scenario? Is there an alternate way to provide keys to clients? And can you revoke clients you no longer want connecting to these relays? BigFix clients know about and therefore can register with any relay they can see on the network. In most cases, this is an acceptable scenario because your relays are usually protected by the network security boundary. But a relay residing in your DMZ might present an easier target for bad actors. If an unauthorized client successfully registers on that relay, they may be able to post false data or perform other actions using unknown vulnerabilities. So a DMZ relay is the perfect candidate for becoming an authenticating relay. Configuring a relay to perform client authentication is as easy as running a task from the BigFix console to enable the option. This can also be done by adding this client setting to the relay and setting its value to 1. A restart of the relay service is required after the option is set. Under normal conditions, when a client first registers in the environment, it requires a key from its parent. If that parent is a non-authenticating relay, that request is passed on to the root server, who issues a signed certificate and key to the client. If the relay receiving that request has authentication enabled, it will reject the request and discontinue communications with that client. So new clients inside the network can get their key by communicating with any of the non-authenticating relays inside the network, but a client that can only reach an authenticating relay is stuck. In such cases, a manual key exchange must be made. First, you need to establish some trust between the new client and the relay. This can be done using a password. The password is stored in this client setting on the relay, and may be a reusable one, which tends to be less secure, or a list of one-time passwords can be created and placed in a file on the relay. Clients registering will need to know which is the next password they can use in order to get the key and register. Once the password is established, there are two ways the client can be registered. Either execute the client binary with a register argument, the password, and the relay's URL, or add this client setting to the client settings.cfg file. As with the first option, the password and relay URL must be specified. When the client runs for the first time after install, it will use this information to request a key and register. And lastly, what if the device is lost and you don't want to take the chance that it will fall into the wrong hands? Well, you simply revoke that client certificate right from the console. In order for a revoked client to re-register, it must be connected to a non-authenticating relay, and presumably this will only happen if it comes into your secure network to do so. Although this brings us to the end of this short webinar, there are still many features in the platform that we've left unexplored. If you'd like to learn what some of those are, join us on one of our instructor-led courses by going to the URL on this page, or just scan the QR code.